Little notes on neutral point. Okay. What is neutral point? We have seen that neutral point is that XAG location at which the aircraft becomes neutrally stable, or dCm by dCl equal to 0, or dCm by d alpha equal to 0, right? And so far we have been talking about neutral point where only wing, tail, and some fuselage contribution, although we have not computed anything, but we have never mentioned about the effect of engine, effect of type of engine the aircraft is flying with. So we'll take effect of engine. We'll take only one case, propeller driven engine, right? What will be the effect of having an engine in the nose? And more precisely the question is, if this is the N0 fixed, that is stick fixed case with power off, then do you think N0 will change with power on? So do you think the N0 will change with power on? That means when you switch on the engine for a typical airplane of this configuration. Suppose nose mounted engine like this. For this case, I repeat the problem. We are trying to understand the effect of thrust or engine on the neutral point. This is the case, power off, that is no power is there, no engine is being rolled, and I'm more focused to this sort of a nose-mounted engine. Without this being on, if this is N0, now the moment the power on case comes, power on, so what will happen? Will the neutral point still remain at some point, let's say here, or it will try to go backward or forward? That is the question. Or indirectly, what is the question? With the engine on, whether the aircraft will become more stable or less stable. Because we understand if N0, let's say N01, and this is N02, the another aircraft N02, then I know that this aircraft is more stable than this aircraft because it has got a large static margin for a given CG location, isn't it? For a given CG location, this aircraft has this much of static margin, and this aircraft has larger static margin. Okay? So I would like to know now what happens if thrust is on. Will there be any modification on the N0 stick fixed? Okay? Let's see. One thing we understand, if running of this propeller adds more stabilizing effect to the airplane, then our N0 fix should go backward. So it will become more stable. If adding this nose-mounted engine, if it contributes towards more destabilizing, then this N0 point should shift this way. Clear? Because then it will become less stable. So now what happens, see, if this is the propeller moving and some delta alpha if it is seeing, then you know that by momentum exchange there will be a thrust generated small though in this direction, because some momentum exchange will be there, one this direction and this direction. So this force, which is proportional to alpha, is now acting ahead of CG. Okay? So this will give any component or any force which are ahead of CG, that will give destabilizing effect, right? So this configuration will give a destabilizing effect. So the neutral point fixed will now, with power on, N0, power on, will come forward here instead of power off is here. Is it clear? Again I repeat, because of this engine thrust or engine power, this is a propeller driven airplane. If there is an angle of attack, there will be momentum exchange in this direction also. So that will give a force. Roughly I can write this function of alpha, and since this force is ahead of CG, CG somewhere here, for any positive alpha, it will give a nose-up moment. And nose-up moment means it is destabilizing for a positive disturbance of alpha. So this will contribute towards destabilizing effect. And hence, the aircraft will become lesser stable compared to power off. So the neutral point will shift here. So this is the point where I write n naught or n naught bar or xn naught or xn naught bar. This is power on and power off is here. Clear? So when you are flying, you have to ensure that a CG should not go beyond power on. Then it will become unstable during power on. Right? Is this clear? That is the definition of neutral point. If this is a neutral point, whether it's power on or power off, point is if the CG goes beyond the neutral point, the aircraft will become statically unstable. So now you know when the engine power is on for this sort of a configuration, then actually neutral point is not what is I'm writing here. With power of case, it will be power on case, little ahead of it. So I must ensure that the CG of the aircraft should never go beyond n naught power on. So this will limit the case how much backward I can take the CG. Okay? So CG backward and CG forward. So how much backward I can take, that is dictated by primarily by n naught power on. Clear? Okay? Now next question comes, how farther forward I can take the CG? Because I know if n naught is here, I put CG here, I put CG here, I put CG here. In all the cases, it will be statically stable. Only thing is if it's the 1, 2, and 3, the third case will be the most stable case. This is little less than the third case, this is little less than the second case. But third case will be the most stable case. Now who decides that? Can I put the CG anywhere in the front? Because I give a logic. If it is CG in forward of neutral point, it will be statically stable. So how does it matter to me? It will be stable. Let it be more stable. But we know fundamentally, if an aircraft becomes highly stable, then I need to put large control deflection to trim it for different CL. How do I know that? One is by simple common sense. If something is highly stable, it will always resist any change which is trying to change its equilibrium to another equilibrium. So you need more effort, right? But mathematically or expression wise, whatever we have developed, we could see here. Again, this expression comes to our rescue. You know that delta E trim or delta E required is delta E naught plus D delta E by DCL into CL trim. This is also CL trim. Okay. And what is this? This is delta E naught plus minus XCG minus XN naught bar divided by CM delta E, right, into CL trim. This is equal to delta E required. So as I am taking CG forward, suppose this is the airplane and CG I am taking forward in this direction. So this gap XCG minus XN naught is going on increasing. Okay? Negative, negative, positive and negative. So what is happening? As it goes on increasing, the delta E required also will go on increasing. Right? And there will be a limit beyond which you may not have a realistic delta E available, because delta E also have a maximum value of deflection, maybe plus minus 25 degrees. Beyond that, the flow will stall over the deflection. This is the elevator, let's say. So beyond 15 degree or beyond 25 degree, depending upon what sort of elevator you are using, the flow may separate. That is why every airplane is characterized with delta E max is plus minus, let's say, 25 degree. Some high fidelity aircraft may have 30 degrees, 45 degrees, but for most of our normal airplane, it is 15 to 25 degrees, depending upon what sort of technology you have used. So the point is, there is a delta E max. You cannot exceed that, okay? But if you go on making it, this separation larger and larger, or making the aircraft more and more stable, this value may exceed the limit given by there. So you have a restriction on how far you can put the CG forward, because beyond a point, this value has become so large that delta E may become more than the delta E max required. Typically, delta E up required. Okay. If I am moving the CG towards nose of the airplane, that is, we are making it more and more stable as I am moving the CG forward pictorially. If I draw delta E versus CL trim, right? This is one case, highly stable. Another case, let's say another case I take. Okay. What is the understanding here? In which case CG is most forward? This is the CG. XCG is most forward because the slope is the highest here, most negative. Then this is XCG2, I call it XCG3. Now see, suppose you want to trim at this CL trim value. So for CG location, let me draw it for you. This is XCG3, this is 2, and this is 1. Right? So this is the most forward, right? This is 1 here, right? Most forward 1, that means neutral point may be somewhere here. So this is highly stable, most stable in this configuration. So now if I want to trim an aircraft for a particular CL trim, you see if I am using these 3 locations where the static margin is least, I need only this much of delta E negative, that is delta E up. Okay? But if I change the CG to CG from CG3 to CG2, and the stability has changed, you see now I require from here to here this much of delta E required, which is again negative, right? This much. It is much more compared to this value. What will happen for this case, if I draw it like this value will be exceptionally high. So what is the meaning? Meaning is you may somehow generate CL trim, okay? But how much CL trim you can trim actually by elevator deflection is decided by what is the delta E max available, and hence directly it also tells you what is the maximum forward CG you can put so that your aircraft is trimmable. Okay, so the aircraft is trimmable means so that I can trim the airplane for that CL. Okay, that is very, very important. So the most forward CG is primarily dictated by most forward CG plus delta E max available. There decides what should be the most forward CG. And most aft CG is divided by N naught, which is power on case. If power off is somewhere here, power off, we have already seen, N naught, power off. So now two distinct things are here. One is aft CG is more governed by N naught, power on, stick fixed neutral point, power on, and forward CG is dictated by what is the delta E max available for all practical purpose, right? You may also wonder what happened during landing when I am actually flying at a higher CL, but the propeller is also rotating. You may wonder what is happening if I am coming for a landing where CL is also maximum, but power is not on in a true sense, it's not a full power. In theoretical sense, I can say propeller windmilling, right? Then what happens? How do I take care of that? So as far as this course is concerned, let me tell you how should I perceive and how should you will perceive. So far what we have seen, this is the N naught, the stick fixed, we are all talking about stick fixed, right? And power off. If the engine is nose mounted engine, then it will give destabilizing effect. So your N naught power on will come here. Power on will be ahead of N naught power off. So I should plan that the CG of the airplane should never cross this. Then it will become statically unstable during power on mode. The next question came, how much forward CG I can allow the layout designer to put? There I realized that forward CG is dictated by that delta E available. So delta E max, that will decide how much really how much forward CG I can trim, because after all it will give more CM, so I have to have any elevator power to control it, to nullify it. So this part we have seen. Now second question, which I was of course whispering, is propeller windmilling. Windmilling, that is, especially during landing, it's not a full power, it's probably just windmilling. So that case, if you see propeller windmilling, it is neither power on but nor power off, right? So it is between these two. So N0 power windmilling should come somewhere here. Propeller windmilling should come somewhere here. So especially during landing, I should be careful about it, because that time N0 is somewhere here. N0 is not power on, it is a little behind, but ahead of N0 stick fix. Do you understand this or not? N0 power on, that time it is contributing full destabilizing effect for a propeller engine in the nose of the airplane. But windmilling, it is in between power on and power off. So somewhere here it will be there, right? So for all practical purpose, during landing, this will be the limit of CG. Beyond this CG, it will become unstable. But for forward, most forward CG, this is most forward CG, when the airplane is approaching like that, it is at a high CL max value, and we need to know that I have enough delta E max, we should be able to trim that CL, okay? Because what will happen, as I move the CG forward and forward, delta E max requirement will go on increasing, we have seen that. And since there is a limit on delta E max, say plus minus 25 degree, so it will be more CG, forward CG will be more governed by this. So this is the limit I am putting here. And if you know these three, four things, you will be able to handle this sort of situation. As we progress, right, when you go for a little bit on stick free, we'll again come back to this neutral point and again address these things from designer's perspective. We'll solve a problem and we'll try to get feel for this. As I have been promising that once some theory based background is ready, then we will be solving some numerical problem to get better insight of those expressions. One of the derivation we made was dCm by dCl equal to minus static margin, right? Static margin. Many books may also refer this as stability margin. And we know meaning of stability margin is if this is the neutral point, if this is the CG, I'm measuring from some reference here, then this is static margin. Of course, this is expressed as a percentage of mean aerodynamic chord, okay? Right. Like this. We are now trying to see this, how to utilize this dCm by dCl equal to minus static margin and get some insight about design. Once I am writing like this, I understand that Cm is expressed as Cm at Cl equal to 0 plus dCm by dCl into Cl, okay? This is the expansion. For a symmetric aerofoil, how do we write? We prefer, if I want to write in terms of alpha, I write Cm at alpha equal to 0 plus dCm by d alpha into alpha. This is workable for symmetric aerofoil. But when I am having a cambered aerofoil, then I prefer to press Cm as Cm at Cl equal to 0 plus dCm by dCl into Cl, okay? Now, once we understand, let's do a problem. The problem is this. Let me write. Slope of CM versus CL is 0.08. Then CM at CL equal to 0 is, let me correct. Slope of CM versus CL is minus 0.15, because initially I wrote 0.08. If it is a positive, it is statically unstable, right? So minus sign, okay, yes, it's statically stable. And what it's telling is CM at CL equal to 0 is 0.08. So you could see that CM naught is greater than 0 and dCm by dCl is less than 0. So statically stable, and since the CM naught is positive, it can be trimmed at a positive angle of attack. Okay. The question is, determine the trim lift coefficient, that is CL, if CG is XCG by C bar is 0.3. Let me again repeat the problem for you to understand. The slope of CM versus CL is minus 0.15. That is, dCm by dCl is minus 0.15. So I write dCm by dCl is minus 0.15. So this is statically stable case. And CM naught, that is CM at CL equal to 0, is 0.08. So it is possible to trim at positive alpha. Question is, determine the trim lift coefficient. What is the CL for which it can be trimmed easily without doing anything else? So what I am to draw is CM, CL, the slope dCm by dCl is minus 0.15, and CM, this value, CM naught or CM at CL equal to 0, this value is 0.08. What is this value? CL trim. That's the question. Very simple problem. You know the slope of this line, you know this. So the CL trim, I can easily find that like 0.08 by, let's say this is x, by this x is 0.15. The slope is negative, I have taken out the negative sign. So x I will get as 0.08 by 0.15, and which is approximately equal to, you can check, around 0.52 or 0.53. So this is the value of CL trim. I even need not solve. Once I draw it like this, from this triangle, right angle triangle, you can easily find out if this is 0.08, the slope is minus 0.15. Slope is nothing but perpendicular by base, and negative sign you have to take here, and that gives you the value of CL trim. So straightforward. Okay? And see how efficient is this expression dCm by dCl equal to minus static margin. With this problem, we will now go a little further and try to extend its value. When you are designing an aircraft, typically if you are designing a civil airplane, you design for a particular static margin, maybe 10% static margin. That is 10% of the mean aerodynamic chord. Okay, 10% of that. So now, if you want to select what is the wing area required, or what is the CL I should design for, you have a criteria. Like for CL, typically I can write L equal to half rho V square SCL. Okay. So, and this is equal to weight, because lift equal to weight. You know what altitude I want to fly, you know what speed I want to fly, you have a wing area. So you typically get some sort of a CL value, let's say CL 0.6. Let us say CL 0.6 you have got. So what is the meaning of this? 10% static margin, right? And CL 0.6, so I write here CL 0.6, and draw a line minus 0.1, get 10%. So dCm by dCl is minus 0.1 because it is 10%. and then find out what is the intercept. So this will be 0.06. Now what I do? I know Cm naught equal to Cm naught of wing plus Cm naught of tail plus Cm naught of fuselage. So I ensure the wing, tail, locations, their area are such that the sum of these three quantity adds up to give 0.06. And the neutral point and CG, they are located such a way that their static margin, that is neutral point and CG, this gap is 10% of mean aerodynamic chord. So how simplified your approach becomes once you use that relationship. You will know this when we do the design course. Maybe we will be doing in one of the books. But it's better that you should not only know how to find delta E for a CL trim, you should also know why we are doing this. So these examples are given to excite your mind that you start thinking in terms of utilizing this relationship for designing an aircraft. Okay? Thank you very much.